but they can't actually see the underlying sensitive information. Zama's answer to this seemingly intractable challenge lies in a powerful and sophisticated combination of advanced cryptography, fully homomorphic encryption, or FHE, multi-party computation, MPC, and zero-knowledge proofs, ZK. These three formidable technologies are the foundational pillars that make Zama's privacy layer not just possible, but incredibly robust.
Now, let's peel back the layers and truly unpack that cryptographic power trio. Is where Zama really showcases its technical prowess. First up, fully homomorphic encryption, or FHE. When I first heard about this, it sounded almost like something out of science fiction, the idea that you could perform calculations on encrypted data without ever decrypting it first. It's like having a magical locked box where you can reach inside and perform complex mathematical operations, say adding numbers or even multiplying them, and the result is still encrypted, still in the box, waiting to be decrypted later by only the authorized party. That's essentially what FHE achieves.
It really is quite something.
So to define it a bit more formally, for those familiar with the technical side, FHE is a groundbreaking form of encryption that enables direct computation on ciphertext, the encrypted form of your data, without ever needing to see the plaintext. For Zama, this relies on advanced schemes like TFHE, where arithmetic operations on encrypted numbers yield an encrypted result that, when eventually decrypted, is exactly the same as if you'd performed the operation on the original unencrypted numbers.
That's a core magic right there.
Absolutely. This capability is crucial because it means your sensitive information, be it a token amount, your identity attributes, or a private vote, remains confidential, even during processing by public blockchain nodes or validators. They can execute the necessary computations to update a smart contract state, but they never see the plaintext data. Zama leverages this with its FHEVM library, a powerful set of tools that allows developers to write confidential smart contracts directly in Solidity, the same language used for Ethereum. This significantly lowers the barrier to entry, making this complex privacy technology much more accessible than you might initially think. This is truly the core innovation, enabling data privacy throughout the entire transaction lifecycle on a public blockchain, from initiation to final state.
That FHE capability sounds incredibly powerful, doesn't it? But there's always a critical challenge that emerges when you encrypt data. Who holds the key to decrypt it? If a single central party holds that master decryption key, well, that creates an unacceptable single point of failure, fundamentally undermining the decentralized ethos that blockchains are built upon.
Right, totally defeats the purpose.
Exactly. This is precisely where multi-party computation, or MPC, comes into play within the Zama protocol. MPC is crucial for decentralized key management through what Zama calls its Key Management Service, or KMS. Imagine you have a highly sensitive secret like the master key to decrypt all your private data. Instead of trusting one person with it, you cryptographically split that key into many pieces. Zama's KMS is comprised of 13 decentralized nodes, and the critical part is that no single node, or even a small group of them, ever holds the full private key.
Okay, distributed security.
Yes. Instead, a threshold of 9 out of these 13 nodes is mathematically required to collaborate to perform any decryption. This robust, distributed setup means that even if, say, 8 nodes were compromised or decided to collude, they still couldn't access or compromise the full private key.
Pretty resilient.
Very. It drastically reduces the risk of a single point of failure and ensures that sensitive information remains secure and decentralized, aligning perfectly with the core principles of blockchain technology while drastically reducing inherent risks. Zama specifically notes that these nodes can be hosted in highly secure environments like AWS Nitro enclaves, which add an extra layer of hardware-level security, further fortifying the system against potential attacks.
Building on that, the final piece of this sophisticated cryptographic puzzle is zero-knowledge proofs, or ZK. This might sound like something out of a spy thriller, maybe?
A little bit.
But the core concept is quite elegant and incredibly useful in the blockchain context. It allows you to prove that you know something, or that a computation was done correctly, without actually revealing what that something is or how the computation was performed. It's about providing cryptographic assurance without exposing the underlying data itself.
Prove it without showing it.
Exactly. In the context of Zama, ZK proofs play an absolutely vital role in validating the integrity of encrypted operations. They can verify that encrypted inputs are correctly formed and that computations performed on that encrypted data are valid without revealing the underlying sensitive information. So for instance, if you're making a private trade on a decentralized exchange powered by Zama, ZK proofs can verify that the trade was executed according to the smart contract's rules. that you had sufficient funds, and that the calculations were accurate, all without disclosing the specific token amounts or even the assets involved.
Which is huge for trust.
Absolutely. This significantly enhances security and trust across the network. It's like being able to show a tamper-proof receipt for a secret transaction where you could prove its legitimacy and correctness, but no one can see the specific details of what was exchanged. This maintains the public verifiability that blockchains rely on, even in a private context.
And what's truly fascinating, I think, is how these three complex cryptographic primitives, FHE, MPC, and ZK, are harmonized to create a truly robust and comprehensive privacy solution. Individually, each is a field of deep research, but together they form this intricate symphony of security, really.
A symphony, I like that.
Yeah. Fully homomorphic encryption is the core mechanism that encrypts your data and enables computations on that encrypted data without ever exposing it. It's the engine of confidentiality, ensuring the locked box remains sealed even while work is being done inside. Multi-party computation then steps in to securely manage the decryption keys in a decentralized way, ensuring that no single entity can unilaterally unlock your private information, distributing trust across a network of nodes.
Okay.
And finally, zero-knowledge proofs act as the unblinking verifying eye. They allow the public blockchain network to cryptographically confirm that all the encrypted computations were performed correctly and honestly without ever needing to see the underlying data itself. This combined approach delivers true end-to-end encryption while preserving the trustless and verifiable nature that makes blockchain so powerful in the first place, allowing for both privacy and public accountability.
Now that we've peeled back the layers on how Zama works under the hood, the symphony of cryptography, let's zoom out from the mechanics and really consider, what does this power unlock? What were you trying to build or do that was impossible yesterday, but is now entirely feasible with Zama today? Let's talk about the game-changing features that fundamentally alter how we build and interact with dApps. First, and most centrally, is that core promise, end-to-end encryption. Zama meticulously implements this by encrypting transaction inputs and contract states directly client-side. Using its FHEVM library for EVM-compatible chains, this encrypted data is then passed to and processed by the blockchain network. And crucially, the results also remain encrypted throughout the entire computation and storage process. That persistence is key. It is. This means sensitive data, whether it's specific token amounts, sensitive user identities, or the details of a private bid in an auction, is never exposed in plaintext on the public ledger. It remains confidential, accessible only to explicitly authorized parties who have been granted specific decryption permissions. This is a monumental shift from how public blockchains typically operate.
And the benefits of this true end-to-end encryption are genuinely unprecedented, opening doors to use cases previously deemed, well, impossible. For one, you gain unparalleled privacy. Unlike traditional blockchains where every detail is public, Zama ensures that sensitive data like exact trade amounts, specific user identities, or the nuances of private voting choices remain fully encrypted from creation to conclusion. This is absolutely critical for real-world applications in private decentralized finance, secure voting systems, or granular identity management, where exposure could lead to financial exploitation, surveillance, or severe privacy breaches.
And what's remarkable is that this doesn't come at the cost of public verifiability. Despite all of this deep encryption, the correctness and validity of computations can still be publicly verified using those powerful zero-knowledge proofs we discussed.
Right, the ZK proofs.
This means the blockchain's fundamental trustless nature is maintained. You can be absolutely sure that the encrypted operation was valid and executed correctly, even though you can't see the specific details of the underlying data. It's truly having your cake and eating it too, isn't it?
It really feels like it. Furthermore, Zama offers quite seamless integration into existing developer workflows. Developers can use Solidity, a language they're already familiar with, alongside the FHEVM library. This means they don't have to learn entirely new programming languages or adopt entirely new paradigms to build sophisticated, confidential smart contracts.
That's a big deal for adoption.
Huge. This compatibility allows encrypted dApps built with Zama to interact directly and composably with existing dApps, established tokens, and widely used protocols, fostering much broader adoption and encouraging innovation within the current Web3 ecosystem.
And this essential privacy isn't confined to a single blockchain. Zama provides true cross-chain privacy. The encryption persists across different chains, whether it's Ethereum, Solana, or other networks.
Yeah, no bridging needed, basically.
Yeah, right. That's a crucial distinction. There's no need for users to bridge assets to a new, isolated privacy chain, which often introduces complexity, liquidity fragmentation, and significant security risks. With Zama, your privacy travels seamlessly with your data and assets across the entire multi-chain landscape.
Finally, a hugely important benefit for real-world and institutional adoption is programmable confidentiality. Zama's features allow for selective disclosure. This isn't just about hiding everything. It's about revealing only what's necessary to only who's authorized under specific conditions.
Okay, more granular control.
Exactly. This means you can define precise rules within your smart contract that, for instance, allow a designated regulator or an auditor to decrypt certain specific pieces of data for know your customer or anti-money laundering purposes, while the vast majority of other sensitive information remains completely private to the public. This bridges the critical gap between the need for robust privacy and the unavoidable demands of regulatory oversight, making real-world compliance achievable on a public blockchain.
Now, as with any cutting-edge technology pushing the boundaries of what's possible, there are always limitations and challenges to consider. It's important to acknowledge these trade-offs and understand how Zama plans to overcome them. First, there's the inherent computational overhead. Fully homomorphic encryption, while incredibly powerful, is by its nature computationally intensive. It requires significantly more processing power than traditional plaintext computations.
It's heavy lifting, cryptographically speaking.
Definitely. Zama cleverly mitigates this by offloading these intensive FHE operations to specialized off-chain coprocessors that currently utilize GPU acceleration. On their testnet, this allows them to achieve over 100 transactions per second, TPS, for FHE operations. While 100 plus TPS is an impressive feat for fully encrypted computation, it's still lower than the thousands of TPS that non-encrypted chains like Solana can handle, or even Ethereum's current baseline of, 1530 TPS?
Right, there's still a gap there.
There is. Scaling Zama to thousands of TPS to truly match the throughput of high-volume public blockchains depends heavily on future hardware advancements, like field programmable gate arrays or FPGAs and application-specific integrated circuit ASICs, which are much more efficient for these specific cryptographic operations. This is a long-term goal that will require significant investment in specialized hardware development.
Another consideration is developer adoption. While Zama provides excellent tools and familiar interfaces like Hardhat and Foundry plugins, writing FHE-compatible smart contracts still introduces new concepts for developers. They need to understand new encrypted data types, like UINT for encrypted integers, and grasp the specific limitations of operations you can perform on them within the FHE framework.
Like division being tricky sometimes.
Exactly. For example, not all arithmetic operations are equally efficient, and some, like division, might be particularly challenging or require different approaches. There's a learning curve here, and widespread adoption will naturally take time, despite Zama's strong efforts to simplify the process and provide comprehensive documentation.
It's also crucial for listeners to understand that Zama is still in its relatively early stages of deployment. Their testnet is currently live as of July 2025. Allowing developers and early adopters to experiment with building and testing confidential dApps. However, it's important to note, as we discussed, that this testnet is unaudited and explicitly not for production use at this stage. It's a proving ground.
It's still early days for real-world use, yeah.
Right. Looking ahead, the main dApp deployment for Ethereum is planned for Q4 2025, with an ambitious expansion to other EVM chains, and Solana slated by the end of that same year. So, while the vision is compelling, the technology is still maturing towards enterprise-ready deployment.
And finally, a point to always consider in decentralized systems: key management risks. While MPC decentralizes key management across those 13 KMS nodes, the system still relies on the integrity of at least 9 of those 13 nodes for decryption. This introduces a very specific trust assumption. While this risk is significantly mitigated by the use of secure hardware enclaves like AWS Nitro enclaves, and by staking incentives for node operators, where misbehavior leads to slashing of their staked Zama tokens.
Skin of the game.
Right, skin in the game. But it's still a consideration for any highly sensitive application where absolute trust minimization is paramount. It's a trade-off that balances decentralization with practical performance and security.
So let's circle back to composability, because it's a huge value proposition here. This means you truly don't have to choose between privacy and full participation in the broader Web3 ecosystem. You can genuinely have both. Composability, in this context, refers to the seamless interaction between confidential, Zama-powered, and non-confidential, traditional smart contracts.
They can talk to each other.
Exactly. Developers can write their Solidity-based confidential contracts using the FHEVM library, enabling encrypted operations. These encrypted dApps can then interact directly with existing tokens, established DeFi protocols, and even NFTs. For example, imagine a scenario where a major institutional investor managing billions in assets previously couldn't touch DeFi because their trading strategies and large order books would be instantly front-run on a public ledger, compromising their entire portfolio.
Big barrier for big money.
Huge. Zama doesn't just hide the trade. It creates a secure, competitive environment where institutions can execute complex, multi-million-dollar DeFi strategies without fear of immediate exploitation. This isn't just about avoiding a few cents in slippage, it's about unlocking trillions in institutional capital for DeFi, fundamentally altering its market structure. You can have a confidential DeFi contract that settles a series of trades privately, ensuring your trading strategy or specific amounts remain hidden while still updating public liquidity pools or interacting with publicly visible token balances.
So the private interacts with the public seamlessly.
Precisely. This allows for incredibly powerful hybrid applications where sensitive operations are encrypted, but they can still seamlessly integrate with the vast and open Web3 infrastructure. It's about building on what's already there, not isolating it.
That seamless integration naturally leads us to cross-chain compatibility. And this raises an important question about how you maintain privacy when data moves between different blockchain ecosystems, which is increasingly common in Web3. Zama's approach to cross-chain compatibility is quite elegant and, again, avoids common pitfalls. Rather than requiring users to bridge assets to a new dedicated privacy chain, which often introduces significant complexity, liquidity fragmentation, and security vulnerabilities, Zama operates as a confidentiality layer directly on top of existing L1 and L2 blockchains.
That saves really actions.
Exactly. This means that encryption persists across chains. Your encrypted data on Ethereum can be routed and processed confidentially on Solana or vice versa without decryption. The mechanisms behind this include the Zama gateway, which acts as a crucial coordinator. It orchestrates these cross-chain operations, validates encrypted inputs, manages access control lists for permissions, and importantly, securely routes encrypted data, what Zama calls ciphertexts, between different chains like Ethereum and Solana.
The traffic controller.
Kind of, yeah. The FHE integration is also key. The FHEVM library is specifically tailored for EVM chains, and Zama is developing similar specialized libraries for non-EVM chains like Solana to ensure broad compatibility. Furthermore, the decentralized coprocessors, which handle those intensive FHE operations, are designed to ensure consistent privacy and computation integrity across these diverse networks. Combined with programmable confidentiality, where decryption permissions are consistently enforced across chains, Zama offers a truly unified privacy layer that integrates seamlessly across different blockchain ecosystems, unlocking new possibilities for interoperable private applications that were previously fragmented.
Here's where it gets really interesting for practical, real-world use cases, especially concerning compliance.
Yeah.
Programmable confidentiality. This isn't just about hiding everything. It's about revealing only what's necessary to only who's authorized under specific smart contract-defined conditions.
That selective reveal.
Yes. Programmable confidentiality gives developers precise, granular control over who can access specific encrypted data within their smart contracts. The mechanism works through access control lists, or ACLs, which are intelligently managed by the Zama gateway. So a smart contract can be explicitly designed to specify, for instance, that only the recipient of an encrypted payment can decrypt the exact amount. Or perhaps a designated regulator or an authorized auditor can decrypt specific pieces of data related to that transaction, such as the source of funds for KYK-ML purposes. Everyone else on the public blockchain sees only encrypted outputs, maintaining their privacy. Very flexible. Extremely. This allows for highly nuanced privacy settings, far beyond simple all-or-nothing encryption. The benefits are clear and profound. True granular control over data access, which is absolutely essential for regulated industries like traditional finance and healthcare. It enables that crucial selective disclosure for KYK-ML compliance while preserving core user privacy. It basically lets you build dApps that can meet stringent regulatory demands while still providing the robust privacy that users increasingly expect and deserve.
Yeah, it truly balances transparency and confidentiality in a dynamic, programmable way that hasn't been genuinely possible on public blockchains before.
So true.
This profound capability for privacy naturally leads us to a crucial question about practical limits and performance. How does Zama address the scalability challenge, especially given the computational intensity of fully homomorphic encryption?
Right, the speed question.
As we've mentioned, FHE operations require significantly more processing power compared to traditional computations on plaintext data. Zama addresses this through several ingenious mechanisms designed to push those boundaries. Firstly, they efficiently offload those heavy FHE operations to a network of decentralized off-chain coprocessors. These coprocessors do the bulk of the encrypted computation, reducing the burden on the main blockchain. The results of these computations are then verified on-chain using zero-knowledge proofs, which ensures their integrity and correctness without needing to rerun the intensive FHE operation on the main chain.
Verification, not recomputation. Smart.
Very. To incentivize honest behavior and ensure the reliability of these coprocessors, their operators are required to stake Zama tokens. If they act maliciously or try to tamper with results, their staked tokens can be slashed, providing a strong economic deterrent against misbehavior. Secondly, Zama is aggressively pursuing hardware acceleration. They currently employ powerful GPUs within these coprocessors to achieve over 100 transactions per second on their testnet for FHE operations.
Which is a good start.
A significant leap from what's possible with traditional CPUs alone, marking a substantial step towards practical performance. Looking to the near future, Zama has clear plans for even more specialized hardware support, specifically field programmable gate arrays, or FPGAs, and application-specific integrated circuits, ASICs.
The heavy-duty stuff.
Exactly. These are highly optimized chips designed to perform specific cryptographic operations far more efficiently than general-purpose GPUs. They are projected to scale performance to thousands of TPS, making FHE much more viable for high-throughput applications and bringing Zama closer to parity with non-encrypted chains in terms of speed. Lastly, the Zama gateway is meticulously optimized to minimize latency in cross-chain encrypted operations, further supporting scalability in complex multi-chain environments. While the inherent FHE overhead still presents a challenge for raw TPS compared to non-encrypted blockchains like Solana, which can handle thousands, Zama's reliance on these future hardware adoptions is a key part of their long-term scalability strategy to match the demands of mainstream and enterprise adoption.
Okay, let's unpack Zama's architecture, because understanding its individual components helps us really see how everything fits together into this cohesive and powerful privacy layer. The FHEVM library is where developers actually get their hands dirty and begin building.
The toolkit.
Right, the toolkit. It's a Solidity-based toolkit specifically designed for EVM-compatible chains like Ethereum and its various layer 2s. This library fundamentally extends the standard Ethereum virtual machine to natively handle encrypted data types. Think of it like adding new E prefixes to your traditional data types. Instead of an int for an unsigned integer, you'll work with an imint for an encrypted unsigned integer and address for an encrypted address.
Uint address, okay.
Exactly. What's truly revolutionary is that it allows developers to perform standard operations like addition, subtraction, or even comparisons directly on this encrypted data, all without ever decrypting it. This incredible capability is powered by Zama's open source TFHE, or Threshold Fully Homomorphic Encryption scheme. The library is designed to integrate seamlessly with popular Web3 developing tools like Hardhat and Foundry, which streamlines the development and testing process for building confidential smart contracts.
Makes life easier for devs.
For sure. The main challenge for developers, as we touched upon, is a slight learning curve associated with these new encrypted data types. And understanding the specific limitations on certain operations within FHE, for instance, some FHE schemes might not efficiently support operations like division without additional complexity. However, Zama's tools are designed to make it as accessible as possible, bridging the gap between familiar Solidity development and cutting-edge cryptography.
If we connect this to the bigger picture, host contracts are your on-chain entry points for these private interactions. These are traditional Solidity smart contracts that are deployed directly on the blockchain, just like any other dApp contract.
Front door, basically.
Kind of. Their primary role is to manage encrypted inputs and outputs, and they act as the essential interfaces that trigger those computationally intensive off-chain FHE computations we discussed. They also enforce the crucial access control lists, or ACLs, for programmable confidentiality, defining precisely who has the permission to decrypt certain data under specific conditions. Importantly, these host contracts don't do the heavy FHE computation themselves. That would be far too inefficient for the main chain. Instead, they cleverly send the encrypted data to the off-chain coprocessors for processing, and then they receive the results back, which are then verified on-chain using zero-knowledge proofs.
Checks the work.
Right. This ensures that the integrity of the private computations is maintained on the public ledger, even though the actual work happens off-chain. So they effectively bridge the on-chain and off-chain worlds, allowing a public blockchain to interact with and verify private computations without ever seeing the raw data.
Now, if the FHEVM library is where developers write some instructions, The co-processors are the specialized engines that actually execute them. Think of them as the workhorses of Zama.
Doing the heavy lifting.
Exactly. But not just any workhorses. These are highly optimized, decentralized off-chain compute nodes specifically designed to perform the extremely computationally intensive FHE operations. When a confidential smart contract, via its host contract, needs to perform a calculation on encrypted data, it's these co-processors that actually execute those complex mathematical functions in a homomorphic way. Because FHE, by its nature, demands significantly more processing power than traditional plaintext computation, it's crucial. These workhorses are both powerful and trustworthy.
Need to trust them.
For sure. To ensure their integrity and honest behavior, the operators of these co-processors are required to stake Zama tokens. If they act maliciously or try to change the results, their staked tokens can be slashed, creating a strong economic incentive for honest operation. Currently, these coprocessors are GPU accelerated and capable of handling over 100 transactions per second on the testnet. But as we've highlighted, Zama has ambitious plans for future hardware support, looking to FPGAs and ASICs to scale these operations to thousands of transactions per second, significantly boosting overall performance and making FHE viable for high throughput applications.
What's truly fascinating here is how the gateway acts as the central orchestrator, making sure everything flows smoothly and securely across the entire Zama protocol. The Zama gateway is a critical orchestration layer that seamlessly coordinates all the different components we've talked about. The host contracts residing on the blockchain, the powerful off-chain coprocessors, and the secure key management service.
The conductor of the symphony.
I like that. Yeah, its key functions are multifaceted and crucial for the entire system's functionality. It validates all encrypted inputs coming into the system, ensures that only authorized operations proceed, and rigorously manages those crucial access control lists for programmable confidentiality, determining who can decrypt what and when. Perhaps most importantly, the gateway facilitates true cross-chain compatibility by securely routing ciphertexts, the encrypted data between different blockchains such as Ethereum and Solana.
Moving the secret messages around.
Basically, yeah. This intelligent routing ensures that privacy is maintained consistently and securely, even when data moves across diverse blockchain ecosystems, eliminating the need for insecure bridging mechanisms and preserving the end-to-end encryption. It truly acts as the intelligent traffic controller for Zama's private data flow.
So what does this all mean for the critical task of managing the actual keys to your encrypted data? The very ability to unlock all that privacy. That's where the key management service, or KMS, comes in, representing a fundamental piece of Zama's decentralized security model.
The key keepers.
Exactly. The KMS is solely responsible for the secure, decentralized management of all encryption and decryption keys within the protocol. It utilizes multi-party computation, or MPC, across those 13 decentralized nodes we discussed earlier. Critically, a threshold of 9 of these 13 nodes is required to perform any decryption. The 9 of 13 rule, right. This robust distributed setup is designed to eliminate any single point of failure. It means no single node or even a small group of them can unilaterally access the full private key and decrypt your sensitive information. This structure also plays a vital role in enforcing programmable confidentiality. The KMS ensures that only authorized parties, as explicitly defined by the smart contract's access control lists and verified by the gateway, can decrypt specific data. It's a highly secure, decentralized, and auditable way to control who sees what, allowing for granular data access control even over encrypted information.
Absolutely. Each piece we've described, the FHE VM library, host contracts, co-processors, the gateway, and the key management service, is essential, and it's their intricate dance together that creates this powerful, comprehensive privacy solution. The FHE VM library provides the foundational tools for developers to write the confidential smart contracts, extending Solidity's capabilities. These host contracts, deployed on-chain, act as the intelligent interfaces, triggering the heavy lifting of encrypted computation, which are then performed by the decentralized coprocessors using FHE. The gateway serves as the critical glue, orchestrating all these complex interactions, validating inputs, diligently managing permissions via ACLs, and ensuring seamless cross-chain privacy. And underpinning all of it, the key management service, powered by multi-party computation, securely handles the keys, providing that final trustless layer of decryption control and enabling programmable confidentiality. Collectively, these components form the resilient backbone of Zama's privacy layer, delivering true end-to-end encryption, robust composability with existing dApps, and fine-grained programmable confidentiality, truly pushing the boundaries of what's achievable on public blockchains.
Now let's transition from the technical architecture to something tangible. Zama's real-world impact by looking at some truly transformative use cases. First up, finance, particularly decentralized finance or DeFi. The problem in traditional public DeFi is abundantly clear. Every trade, every balance, every transaction amount is transparently visible on a public ledger. This leads to issues like front running, where sophisticated bots can exploit your pending trades, and it creates opportunities for general market manipulation.
Yeah, it's a real headache.
It is. Beyond that, the lack of privacy is a significant deterrent for institutional adoption, as large players cannot expose their proprietary strategies or sensitive financial positions to the public. Zama's solution is elegant and powerful. Confidential smart contracts that encrypt transaction inputs and states from end to end. This means your sensitive financial data remains completely private. Consider some specific, compelling examples. You could have confidential token transfers, where encrypted ERC20 or SPL tokens allow for truly private payments, protecting your financial data from public view without sacrificing public verifiability.
Like private money on public chains.
Pretty much. Imagine private DeFi trading, where automated market makers or lending platforms can process trades without revealing your proprietary trading strategies or specific positions to the entire market. This could unlock massive liquidity from institutions and high net worth individuals previously hesitant to enter DeFi. Furthermore, Zama enables compliance-friendly finance through programmable confidentiality. You can program your contract to selectively reveal specific encrypted data to designated regulators or auditors for KYC or AML purposes without exposing everything else to the public.
The regulatory angle is huge.
Absolutely. This is where it gets really interesting for the future of finance, moving from totally open, exploitable ledgers to privacy-preserving yet auditable transactions. It's a fundamental game changer for mainstream and institutional adoption of decentralized finance.
That ability to selectively disclose while maintaining core privacy is critical, and it leads naturally into another transformative area, digital identity. This raises an important question about how we achieve true self-sovereign identity online, where you genuinely control your data and decide who sees what rather than relying on centralized entities.
Giving power back to the user.
Exactly. In current decentralized identity solutions, sensitive personal data often ends up being exposed on public blockchains, which is antithetical to the very concept of personal data ownership. Zama offers a powerful toolkit to address this fundamental privacy challenge. With Zama, fully homomorphic encryption ensures that your identity attributes like your precise age, nationality, credit score, or medical history remain entirely encrypted. You can still prove a specific attribute, for example, that you are over 18 or have a valid driver's license without disclosing your exact birth date or the full license number, thanks to the power of zero-knowledge proofs for verification.
Prove without revealing. Neat.
It is. This enables several key identity use cases that were previously problematic. Firstly, encrypted credentials mean you can hold sensitive personal information in a private, verifiable way, similar to a digital passport that only reveals what's strictly necessary. Secondly, selective disclosure allows you to grant specific service providers access to only the designated data they absolutely need for a transaction, say your shipping address for a delivery, while maintaining privacy for everything else.
Just the minimum needed.
Right. And thirdly, private authentication means you can securely log into dApps or access services without exposing your full user identity to the public blockchain. Zama empowers individuals to reclaim and truly control their digital identities, making it a critical step towards truly privacy-preserving and self-sovereign decentralized identity solutions.
Beyond the massive implications for finance and identity, Zama's capabilities open doors for a whole host of other fascinating applications that were simply not viable before. Imagine encrypted data analytics. A consortium of hospitals, for instance, might want to research a rare disease. They each hold sensitive patient records, legally unable to share them in plain text.
Right, IPA and all that.
Exactly. With Zama, they could collaboratively run complex statistical analyses, say, identifying correlations between anonymized patient demographics and treatment outcomes directly on the encrypted data. No hospital ever sees another's raw patient files, yet they collectively derive life-saving insights from the combined data set. Or consider private AI model execution. A company has a highly proprietary AI model, and clients want to use it on their sensitive confidential data without sharing that data. Zama allows the model to run its computations on the client's encrypted data, returning an encrypted result, maintaining both the model's intellectual property and the client's data privacy.
Wow, that's powerful for AI collaboration.
It really is. A leap from current solutions which often require complex legal frameworks or data anonymization that risks fidelity. We could also see confidential auctions, where bids remain secret until the auction closes, preventing manipulation and ensuring fair play. Or truly secure voting systems, where individual votes are encrypted to assure voter privacy while still allowing for verifiable tallying and auditability.
So many possibilities.
The possibilities are vast and genuinely transformative when you can finally have robust, auditable privacy on a public blockchain, unlocking entirely new business models and forms of digital interaction. Let's talk about Zama's journey from vision to reality and where they stand today, because it's a rapidly evolving landscape. Their testnet is currently live as of July 2025.
Which is pretty recent.
Very recent. It allows developers and early adopters to experiment firsthand with building confidential dApps and exploring the FHEVM library. It's important to reiterate, as we've discussed, that this testnet is still undergoing rigorous testing and is currently unaudited. It's explicitly not for production use at this early stage. It's a development environment designed for exploration. Looking ahead, the mainnet deployment for Ethereum is planned for Q4 2025, marking a significant milestone with an ambitious expansion to other EVM chains, and Solana slated by the end of that same year. This indicates a clear roadmap towards broader interoperability and availability.
Big plans for late 2025, though.
Definitely. Zama will also feature its own Zama token, which will play a multifaceted role within the protocol. It will be used for network fees, for staking by those crucial coprocessor operators to ensure honest behavior and integrity, and for decentralized governance, allowing the community to participate in the protocol's evolution. The Token Generation Event, or TGE for Zama, is currently scheduled for late 2025. For developers looking to get involved, the tools are already robustly in place. Zama offers comprehensive hard hat and Foundry plugins, extensive Solidity libraries for the FHEVM, and detailed tutorials available through their documentation at docs.zama.ai and on their GitHub repositories.
So the dev resources are there.
They are. So for developers looking to pioneer privacy-preserving dApps, the tools are there, the testnet is live, and the mainnet is on the horizon, creating a clear and exciting path to innovation.
What's truly impressive here, beyond the groundbreaking technology itself, is the significant backing and the caliber of the team behind Zama, indicating strong confidence in their foundational technology and their long-term vision. Zama is a Paris-based open-source cryptography company that has quickly established itself as a leader in this nascent field. They've managed to raise a substantial $130 million in funding to date, which includes a very notable $57 million Series B round in June 2025.
That's serious money.
It is. This round impressively valued the company at over $1 billion, granting it coveted unicorn status. This level of investment from prominent blockchain and venture capital firms like Pantera Capital, Blockchain, Multicoin Capital, and Protocol Labs speaks volumes about the perceived importance and transformative potential of their work. The company was co-founded by Dr. Rand Hindi and Dr. Pascal Pallier, both distinguished figures in the field of cryptography, with a very clear and ambitious focus on making fully holomorphic encryption accessible and efficient for broad adoption across the Web3 ecosystem.
Heavy hitters in the crypto space.
Absolutely. Their combined expertise is genuinely at the heart of this groundbreaking protocol, providing a strong technical foundation and strategic direction.
And the community sentiment really underscores that excitement and belief. Posts on X, formerly Twitter, highlight a strong buzz for Zama's testnet, with many developers and enthusiasts diving in. It's widely described by community members as a game changer for on-chain privacy, with many comparing it to HTTPS for blockchains. A pretty powerful and accessible analogy that resonates widely.
Yeah, it's a sticky one.
It is. Users who've actively tested the Zama testnet note seamless confidential transfers and robust encryption, reporting no visible plaintext data, which directly confirms the protocol's effectiveness in practical scenarios. The buzz is undeniably real, and it points to a strong, widespread belief in Zama's potential to redefine blockchain privacy and truly unlock a new era of decentralized applications, moving from theoretical possibilities to tangible real-world solutions. Today, we really did a deep dive into the Zama protocol, exploring how it's carving out a crucial new path for privacy in the blockchain space. We started by understanding the fundamental problem of pervasive transparency of public blockchains and the limitations it imposes, and then introduced Zama as its elegant solution, cross-chain confidentiality layer. We meticulously unpacked the sophisticated cryptographic power trio that makes it all possible. Fully homomorphic encryption for securely computing unencrypted data, multi-party computation for robust, decentralized key management, and zero-knowledge proofs for verifiable integrity without exposing sensitive information. We then explored Zama's game-changing features, from true end-to-end encryption and unparalleled composability with existing gaps to seamless cross-chain compatibility and the powerful nuanced control of programmable confidentiality.
Covered a lot of ground there.
We did. We also laid out the technical components that work in harmony, including the FHEVM library, host contracts, co-processors, the gateway, and the key management service. Finally, we explored the transformative real-world use cases in finance and identity and caught up on Zama's ambitious journey from vision to its upcoming mainnet reality.
If we connect this to the bigger picture, Zama represents a genuinely significant step towards a more mature, versatile, and ultimately a more adopted Web3. It definitively demonstrates how the immense benefits of decentralization and public verifiability can now be combined with the necessary safeguards of confidentiality and auditability. This isn't just about hiding transactions for the sake of it. It's about enabling a whole new realm of possibilities for real-world adoption, from truly private and compliant financial systems and secure digital identities to confidential enterprise solutions that simply weren't feasible on public blockchains before.
Contracts are your on-chain entry points for these private interactions.
Fully homomorphic encryption scheme. The library is designed to integrate seamlessly with popular Web3 developer tools like Hardhat and Foundry, which streamlines the development and testing process for building confidential smart contracts.
Makes life easier for devs.
For sure. The main challenge for developers, as we touched upon, is a slight learning curve associated with these new encrypted data types, and understanding the specific limitations on certain operations within FHE, for instance. Some FHE schemes might not efficiently support operations like division without additional complexity. However, Zama's tools are designed to make it as accessible as possible, bridging the gap between familiar Solidity development and cutting-edge cryptography.
If we connect this to the bigger picture, host contracts are your on-chain entry points for these private interactions. These are traditional Solidity smart contracts